Hello, everyone. Let's start our lecture today. So this is for pattern recognition. And I am your new instructor, and my name is Robbie Tan, which is different from your previous instructor. So before we begin, just want to make sure that you can hear me. So if you can hear me, can you say something or something like yes on the chat, please?
Yes, sir.
Okay, that's good. All right. Okay, so today is a lecture 7, and there are a few different topics in our lecture today. But one of these, and the first topic that we will discuss is PCA. PCA stands for Principal Component Analysis. Right, so the basic concept of PCA is that imagine that you have a two-dimensional space, right? So for example, this one is X and Y, and you have some data. So imagine that you have data point like this, for example. And of course, you can compute the mean of this, right? So you can compute the mean of this point. And basically, from this mean, the center point of the cloud, of the points cloud, we want to get the first principal axis. And the first principal axis in this case is this one, V1. And we also want to have the second principal component or second principal axis, which is this one, right? In this case, it will be V2. And it described the variance of these points. What I mean by variance is that it described that, for this particular variance, it will be the principal component will be that way. So this is the variance of the data, and the variance for the other one is this one. So there is some variance of the points. And why this is the principal component? So this one is the first principal component. And this principal component has something to do, we will discuss this later on, it has something to do with the first eigenvectors. So this one is the first eigenvectors. And the variance that I mentioned, has something to do with eigenvalue. So this one will be the first eigenvalue. And basically, this is something that we want to learn today. So again, given the input, and in this case, our inputs are some points or samples, which has xn as the representation of the point. This is one point, xn. And we have many of them from 1 up to capital N. So this one is the sample data or sample points in our case. So let's put sample data. And our output will be the principal components. So our output will be the principal components. And these principal components are represented by V1 up to Vm. Okay, so let's look this dimensionality here first. So our data has the dimensionality of t by 1. So one point has the dimensionality of t by 1. Okay, so and t for our example here, for our simple example here, this one t equal to 2. And we want to find the first principles up to m. So this one is V1 until Vm. All right. And in this case, the dimensionality of the principal component is, of course, t by 1. And all this is t by 1. All right. Any questions so far? Basically, if it is a dimensionality reduction, if you want to reduce the dimensionality, for example, later we will learn that we can have m actually great smaller than t, or in general, we can say that m can be equal to as t as well. So this is the purpose of having these principal components, that we want to reduce the dimensionality of the data. Any questions so far? And aside from this principal axis, we also have the variance or the eigen value for each of these. Okay, so this is the input and also the output. So there is a question here from Nitin. Nitin asks, can m greater than t? Well, the answer is no. M is always less or equals than d. So for example, in this case, in our case here, d and m are the same. M equal to 2, t equal to 2. And it's not possible for us to have another m. You know, there's the basic principle of PCA is that it has to be orthogonal. And there is no other orthogonal line aside from these two. Okay. Now, there is a question here, another question from Emil. Emil asks, what is M? Well, M is the index of this M. V1, V2 is the index of M. So in this case, V1 and V2, M equal to 2. T is that this one. T is T equal to 1 for X, T equal to 2 for Y. So in this case, T equals to 2. So now, if you look at this, simple example, you might ask, what does it mean by M? What does it mean by, you know that the meaning of this, right? If it is M equal to T, you know this. This one is exactly this one, exactly the example that we have. But if M smaller than T, what does it mean? All right, if M smaller than D, what it means by that? Well, it means very simple, that it means for our example here, it means that we don't have this one. You remove this one. You remove the second principle. You only have the first principle. Okay, so that's the meaning of M smaller than D. We remove the second principle. So what it all means though, right? So let's discuss about the intuition behind this first, before getting into the mathematical equation. So why this V1 and V2 are interesting, are important, are useful? Why they are useful? Basically, that's the question. Okay, so one of the application of these principal components, as it mentioned, is to have dimensionality reduction. So this one, when we say that M smaller than D, it means dimensionality reduction. Dimensionality reduction. So what does it mean by this dimensionality reduction, right? So let's have an example here, the same example that we have. So let's assume that we have this point. This point have some coordinate system, right? So in the beginning, the coordinate system is x and y. So this one, for example, this point, this particular point there, has a value of x, for example, 1. This one is a value of y1. So you can describe this point, this red dot, as x1, y1. This is what we normally do when we describe a point, when we describe a sample. When we have the principal components, so let's assume that we have the mean here, right? Assume that we have the mean, and then we have this principal component V1. So with this V1, so let's put another drawing here so that it can be more obvious. So assume that this is a V1 and V2. Let's have two of them first, V1 and V2. So with V1 and V2, actually we have another base, another coordinate system. It's like a new x and y. So this is like a new x new, y new here. Of course, we don't really call it x new, y new. We call it V1 and V2. With this V1 and V2 as the new axis, as the new coordinate system, then we can describe this red line, red point with respect to this V1. So this one is, for example, the new coordinate. I'm not really sure what is this called. Maybe any value here, for example, A1. And this one, for example, here, with respect to V2 is a B2. Then we have another representation of that point. So let's call this point C. Right? So let's assume that the name of this point is point C. So C, so now point C can be represented by xy, x1, y1, can also be represented by A1 and B1. So this one is not B2, but B1. Okay, so that's the meaning of this. So we can represent the points now using two coordinate system. The original coordinate system, which is x and y, and the other is V1 and V2. In this case, there is no reduction in dimensionality. We just represent one point using one system and the other system. So now, how can we do the dimensionality reduction using V1? So if you look at V1 for point C, we can reduce it into only A1. A1 is not really the same as C, but it's very close. It's approximation of C. So this is called from 2 dimension, from 2D, now you reduce it into 1D. If you know the principal components, you can have this approximation. Is that understandable, the intuition? So that's the meaning of this, that M smaller than D. Any questions? Okay, so there is a question from Darius. Is it possible for you to upload your already another notes before the lectures? Yes, so there is, I don't really have the note yet with me. So I just finished my notes today. So, and it can be wrong. So I don't want to give a note that is wrong. So I will share the note after the lecture. So then it can be more safe. It can at least less errors in the note, on the note. Okay, so there is another question from Aruvana. Will there be any loss after reducing the dimension? If there's any loss? Yes, there is a loss, of course, as you can see here, Arunava, that A1 is not really precise. A1 is just approximation of C, right? It's not the same as the point of C. It is just close to C. It's actually not C itself. So there is a comment from Darius, it's okay if it is wrong. So Darius, the main problem is that students will blame me if there is a version that is wrong. Because in the exam, they can say that, look, this is your note and this is wrong, and I just follow that one. So I don't want that to be an excuse for the students. So I just want to try to maintain the most consistent version of the note. Okay, so Arunava asks again, is this only describing one features? I'm not really sure, Arunava, with your questions. Maybe you want to speak up on the microphone to clarify your questions.
Yeah, previously it was having A and B, both the dimensions. So now it is only having A dimension. So that's what I was saying.
So what do you mean by features here? We haven't talked about anything about features.
Oh, that was by mistake.
Okay, so again, what is your questions? If it is not features, then what?
The same question. I was just clarifying.
Oh, okay. All right. So yes, for this particular example, we from 2D, from two information XY and X1 and Y1, you have one information, one entity, which is A1 for representing C. All right. So Nitin has a question here. Changing the axis will give us a way to represent higher dimensions into a lower dimension. Yes, Nitin, that's the basic concept of dimensionality reduction in PCA, in principal component analysis. But it might not be true for other different methods of dimensionality reduction. So this PCA, one of the application of PCA is for dimensionality reduction. But there are many applications of PCA, and also there are many methods of dimensionality reduction. And your statement is only true for PCA. Okay, so Linky has a question here. How far we should reduce the dimension? Well, there is no restriction here, Linky. As we look at this equation in the blue highlighted color now, that M is just smaller than D. What is M? M can be 1, 2, 3, 4 until D. There's no restriction yet. Okay, any other questions? Okay, so all right, so let's move on to more technical details of this. So we know the input and we know the output, and I hope that you know also the intuition behind this, why this is useful, at least in the case of dimensionality reduction. All right, so now the problem is that, of course, the question here, the question that we can ask is how to get the eigenvalue and eigenvectors, right? So how to get V1 until Vm given the input, the samples, xn, n equals to 1 until n. So this is the question that we need to answer. Right, so the answer for this, there are two ways of getting to the answers, getting to the output. One is to maximize the variance. So we want to find V1, for example, to represent the direction that maximizes the variance. I will explain this later soon. And second way of processing this is to minimize errors. So to minimize error. So let's look at the first one first. So let's look at this one. Maximizing the variance. All right, so number one, maximizing variance. So in terms of the maximizing the variance, so the basic idea of when we say variance, again, is that we have a sample point. There are many different types of variance here, as you can see. One of the variance is maybe this one, the other is this one, the other is this one. So all this can give you some variance, right? So all this is a possible direction of the that can give you some variance. For example, if I just arbitrarily put or draw this direction, for example, then the variance of this is more or less this one. So this one will be the variance. So this one would be the variance. So put it lambda as a variance, lambda 1, for example, this one. Another possibility is to have this variance here. So in that case, the variance, or sorry, the direction, and the variance will be lambda 2. So if you see here, if you look at the picture that I just draw, which one is greater, lambda 2 or lambda 1? If you just look at the picture, yes. So this one means that the variance of V1, for example, name it is V1, and this one is V2, for example. So in this case, the variance of V1 is greater than the variance of V2. So maximizing the variance means that we try to maximize this lambda. Okay, so that is the intuition behind this variance maximization. So there is a question from email. Email asks, maximum variance is a first principle component? Well, if it is the largest variance, it will give you the first principle. Yes, it is the largest. Okay, so now let's look at the definition, mathematical definition of variance. So let's assume that we have a certain direction, certain axis. And we do not know now whether this is maximum or not. Okay, so let's assume that we have this blue line and this blue line, we want to measure the variance based on this blue line by projecting all the green points on this blue line. So basically, if you look this closely, what we mean by that is that, for example, this point here, we project that into that point. This point here, we project into that point. This one project that point, and so on and so forth. So we have all the projection here. Of course, this is go through here as well. So we have all this projection, and this one from the point of view from the center. So from point of view of the mean here, we measure the variance. So that is the meaning of this operation, that we have to do the projection first. And after we get the projection, we want to measure the variance. So in that case, mathematically speaking, the variance, so the variance here equals to 1 over n, because assuming that there's n points and samples, and this is a sum of over n equals to 1 up to n for all data. Then we transform this one. V1 is the transformation. V1 is the direction, and we transform the data xn. So this one means that this equation means that we transform xn with so this one is xn, this one is xn. We transform this xn into this point. So this point here, the green point now, is this one. Okay. But we have to remember that we have the center point here, the mean in the middle. And that have to be included, because that one means that this one, later on, if we find the second one, for example, this will be the origin of our system, of our new coordinate system. Okay, so this one, it means that minus V1 transpose X mean. So this second equation here, the second equation here is referring to this point there. Any questions? You need to understand this, because if you lost here, then you will not be able to understand the rest. So there's a question here from email. Why do we need to have the subtraction, the minus operation? Well, as I mentioned, Nitin, that the variance is from this point of view. The variance is from this center. Okay. Any other questions? Okay, so yes, that's true. So I just want to emphasize that this is understood first. And if we want to maximize the variance, to get the meaning of the variance, have to be squared. Okay, so any questions here? Any questions? I see a few questions, but I think I already explained, I already answered. If you don't understand, then you have to speak up on microphone.
Hi, Prof. Why
Yes.
do we need to minus X mean again? Is it because I offset or something?
No, you have to know the meaning of this X mean here, the second term. The second term is the red point. It's the origin.
Okay.
This one is become your origin. The red point become your origin.
Okay.
Because the second system, the second coordinate system, which is this one, need to have an origin, right?
Yeah.
So if you want to measure the variance, you need to have some origin.
Yeah, okay, I understand. Thank you.
Yeah.
Thank you.
Yeah. Okay. Any other questions? Again, I already answered this one, all the questions that you have on the chat. But if you are not clear, please speak up on the microphone, on your microphone.
Xn is any random point, right? On that axis.
I don't understand your questions. Random points. What do you mean by random points?
Like the projection from the real data sample.
The real data or the samples will be projected on V1. Yes.
Yes, and that point is xn.
No, xn is the point. This xn is the input. Xn is the input. This xn here, let's put different color. Xn is the input. We mentioned this in the beginning here, right? Xn is the input. So xn here is the input, the point, the address of the points of the samples in x and y coordinate system.
Okay. Yeah, got it.
Yeah.
Thank you.
Yes. Any other questions before we move on? Again, this is a very important expression because we will do the derivation based on this equation. All right. So we know that x mean is quite simple, right? To find this, this one is 1 over n, sum n equals to 1, n of what? Anyone can guess? What is the expression that I have to write there? Yes. Yeah. So this one is xn. So if you look at the dimensionality, this one is d by 1, this one is d by 1. The mean is live in the d dimensionality. By the way, this one, if you look at the dimensionality, here, variance is 1 by 1. And V transpose means that this one is 1 by D, this is D by 1, this is 1 by D, this is D by 1. So in the end, it is 1 by 1. The operation is a scalar operation. Okay. Right. So there is a question from Yan Xuan. Is there any requirements on V1? Well, at the moment, Yan Xuan, there is no requirement. Only this variance that we have so far.
Prof, is V1 a unique vector?
V1 is whether it's unit vectors. It's a good question, but at the moment we don't really have that requirement either.
Okay.
It's not necessary to be unit vectors at the moment, at least.
Sorry, Prof. If it's not a unit vector, right, or it doesn't have fixed length, right, then I can easily have a V2 that is much longer, and then
That's correct. But we will. But now it's not unit vector at the moment. But we will continue soon. That it actually in the end it will be unit vectors.
okay, thanks.
Yes. Yeah. Basically, this one it will be unit vectors because otherwise the variance will not make sense. Okay. Any other questions? Okay. So. Right. Now let's move on. From this one, let's get the meaning of this. So for this particular expression, for this green expression here, let's expand this further. This means that we have a transformation projection of T xn minus x mean. This is the same thing, right? You do the subtraction in the original space, and then do projection. It's the same thing. Okay, so and we know that a b square equals to a square b square. So in other words, we can expand this further. So here, if we expand this further, we can have phi1 transpose square multiplied by xn minus x mean square. Well, this is not really a good way of squaring, because this one is, this one is actually 1 by d is a factors, and this one is a d by 1 is also a factors. So a factors cannot be squared. So this is an abuse of notation here. So I will do it more properly now. So the more proper expression will be phi1 multiplied by xn minus x mean multiplied by xn minus x mean. So this is a square in factors transpose, right? Multiplied by phi1. Somewhere that have to be transpose. Again, in the end of the day, it have to be 1 by 1. So this one is transpose. So again, if you look at the dimensionality here, this is 1 by d. The whole thing here is d by 1. This one is 1 by d. This one is d by 1. So in the end, it is 1 by 1. Any questions so far? Any questions, anyone? Okay, so let's move on to derive this further. Now we have this one, and remember, actually in our variance, we want to maximize the variance. So here is, if I put the variance whole equation, then I have to write 1 over n. So this is variance now. 1 over n sum over n. So if you look at this equation, the last equation, this guy or this variable, these two variables are independent from n. There is no n in this phi1. So because it's independent from phi1, I can just take this phi1 out of the sum. So I can write phi1 transpose 1 over n sum over n xn minus x mean multiplied by xn minus x mean transpose phi1. Okay. Any questions so far? Well, it's just a derivation, right? It's quite obvious. So this one is a phi1 transpose. So now the whole things here, can be defined as a new variable s. So this is our last equation. This is quite important equation here. Okay, so when we say that we want to maximize the variance with respect to V1, because we want to get, we do not know V1. That's why we want to maximizing the variance with respect to V1. It can be written as, so this one is hence maximizing the variance of V1 transpose as V1 maximizing over V1. So these variables here, these variables here, S is known. So this one is known. V1 is unknown. V1 is actually the output that we want to have. Okay, so remember that this one is 1 by d, this one is d by d, this one is d by 1. This is now becomes our most important equation. Any questions so far? So if we do this, what will be the easiest solution for this? If we do this, what will be the easiest solution? Anyone? What will be the easiest solution for this problem? What will be V1? Any guess? No, I mean, what is V1 to solve this problem, to solve this maximization problem? What will be V1? Well, don't think too much yet. It's very simple. Intuitively, will be V1 to maximizing this? So maximizing this, what will be the limit of maximizing this? It will be infinite, right? If you want. If you want to maximizing the variance, you can have the infinite value there and the output. If it is infinite, what will be V1? What will be V1 if the output is infinite? Anyone? Well, the easiest one is that we can find V1 when the magnitude of this equals to infinite. This is called trivial solution. Any V1, as long as the magnitude is infinite, that will be the answer for this. This is called trivial solution. Any questions? Makes sense, right? Because you want to maximize this equation. Of course, there is no bound for maximizing this, and it can be infinite. And that's why if it is infinite, then the magnitude of V1 will be infinite, and it can be any V1 as long as the magnitude is infinite. But we don't want to have this, right? We don't want to have this. So we don't want to have the output infinite because it doesn't give us any value of V1. So we want to try to avoid, this trivial solution. We don't want to be trapped into a trivial solution. So if you don't want to be trapped into trivial solution, what do we do? So the question here, if you don't want to be in this way, what do we do? We have to put constraint, right? Or equalization, but actually what should be constraint? We have to put constraint here. What is the constraint? Yes, the constraint should be that the magnitude of V1 have to equals to 1. In other words, V1 has to be unit factors. Exactly. So this is why in the beginning we didn't mention any constraint of unit factors. But when we face with this situation, we are forced to use unit factors, because otherwise it will be trapped into a trivial solution. Any questions? So this V1 the magnitude of V1 equals to 1 as unit factors. This also implies that V1 transpose V1 equals to what? V1 transpose V1 equals to, yes, equals to 1. So this one is a subject, maximizing this equation, subject to V1 transpose V minus 1 equals to 0. Any questions? Any questions? Anyone? Okay, so if there is no questions, our next question is that how to solve this problem, right? How to solve. Okay, so now let's look at the solution of this. Okay, so the solution is based on, some of you actually already mentioned this, using Lagrangian multiplier. If you convert this into Lagrangian's multiplier, it means that let's assume that this one L, let's see. Okay, so let's assume that this one is maximizing. Let's assume that we want to maximize over V1 on L function of V1. And L is the same as, if you use Lagrangian, it will be V1 transpose S V1 plus what? Anyone knows? If you use Lagrangian multiplier, then what is the second term? Well, the second terms will be mostly the constraint. And putting the constraint, we have to multiply it with Lagrangian multiplier. So lambda 1 here is a Lagrangian multiplier. Yes, that's already mentioned by Shicha. That we have lambda 1 with multiplying with the constraint V transpose V minus 1. Okay, so again, L1 here is actually 1 by 1. So the whole things here is 1 by 1. This one, the whole things here is 1 by 1. So in other words, L lambda 1 is a scalar. So this one is 1 by 1. This one is 1 by 1. Any questions? Okay, so if there's no questions, maximizing L means what? So if you want to maximize L here, what do you need to do? Anyone? What do we need to do next if you want to maximize L? Yes, the derivative. And derivative equals to what? The derivative equals to 0. That's right. So dl v1 over dv1 bar equals to 0. Okay, so this would be solvable because our loss is actually square. It's actually quadratic. So it should be solvable. Okay, so by the way, before I move on, what is the dimensionality of this? What is the dimensionality of this term? Anyone knows what is the dimensionality of this derivative? Anyone? Yes, d, not d by d. This is actually d by 1 because following the the dimensionality of V. L here is 1 by 1. L itself is a 1 by 1. But the whole thing is D by 1. So the 0 here is actually 0 bar, which is 0 factors. And this one is a D by 1. Okay, so this one, you can just do the derivative of this. So you just consider this one. And based on that one, you do the derivative. The derivative of this with respect to V. So this will be simple, right? So you have V square multiplied by S. So you will have 2S V1. So this will be correct because this one is a D by D, this one is D by 1, and we have D by 1 as the output. Plus, this one is a V transpose V, which is a V square, right? V square means that you have 2 lambda 1 V1 transpose equals to 0. Again, this one is a 1 by 1. This one is a D by 1. Okay, so this is the equation that we want to solve. And based on this equation, we will have S V1, because 2 can be cancelled. Let me think. Is this is correct, right? Let me see.
V1 transpose, right? At the end.
Sorry?
At the end, V1 transpose, right?
Why this V1 transpose? Why the transpose is needed?
Because 1 cross 1, and that should be 1 cross D.
Sorry, I don't understand. Which
The
one you are
dimension.
talking? The last equations or which one?
Last equation. 2 lambda 1 V1. The dimension is not matching.
V1 is D by 1, right?
So the multiplication has 1 cross 1 cross D cross 1. That will not cancel.
No, this one is this one. This one here is like A or maybe you 2 multiplied by 1, 2, 3. It's okay, right?
Yes.
Yeah, it's okay, right? It's no problem here. This is 1 by 1. This is the 3 by 1.
First one has D cross 1 multiplication.
Sorry, I don't understand.
First one has D cross D and multiplying with D cross 1. So that will result in D cross 1. But the second one has D cross 1. Okay.
So D lambda here. So lambda here, assume that is 5. Lambda equal to 5. Yeah. Lambda here equal to 5.
Yeah. That is correct. Yeah.
It's okay, right?
Yeah.
Yeah, there's nothing wrong with this, right?
Mm-hmm.
Okay, there's nothing wrong with this. Wait a moment. So let me check if everything is fine. Oh, so by the way, that's a textbook. The textbook is actually it's called Pattern Recognition and Machine Learning. So that's the textbook that I use here. So you need to read the textbook so then you can understand what's going on here. There's something wrong actually that I'm writing here. Yeah, so there is the equation here is not nice. So this one is not wrong, but it's not nice because this one is become minus lambda 1 V1, right? So this is not really nice because this one is not something that we want. So because this is not something that we want, it's not, not nice. I will say later on what is nice and what is not nice. But anyway, so we don't want to have the minus there. If we don't want to have the minus, so we have to modify our original equation here. So this one here, actually I can write in this, there's no change in terms of the meaning. If I write this in this way, there's nothing in the, prevent me from writing in this way. Correct? So in that case, it will be nicer. I will show you why this is nicer later. So this one is, I will change this into 1 minus V1 transpose V. And this one is actually answering your Darius comment in the beginning. Actually, in my lecture note, it is wrong. It is not in this way. It will create you the minus, right? So this one is, I have to correct this. So this one is actually minus here. So it will be nicer because that will be no minus. So this one is the correct one. So in this case, it will be nicer because what is this? What kind of equation is this? Some of you must know about this equation already. What is this equation? What the kind of definition is this? Anyone can see that? Yes, this is the equation for eigenfactors and eigenvalue. This is exactly the definition of eigenfactors and eigenvalue. That's why I call it nice. Nice because, nothing wrong with the minus, but it would be nicer to have this form because this is the exact definition of eigenvalue and eigenfactors. So therefore, lambda 1 is the first eigenvalue and V1 is the first eigenfactor. So maximizing the variance that we did in the beginning will lead us into this first eigenvalue and the first eigenfactors, assuming that we only have one line. So assuming that we only have one projection, V1. Okay. Any questions? Any questions so far? Okay, so there is a question from email. How can we get the textbook? The textbook actually available online, the PDF, but you can also, find in the library. It is again called the textbook. Name is Pattern Recognition and Machine Learning. By Bishop. And this one, the discussion that we have is actually chapter 12. So this one is a chapter 12. Okay, any questions? Any other questions before we move on? Okay, so in our equation here, the discussion that we have, we only assume this only one V1, right? Now the question is that if we want to have all the eigenvalues and eigenvectors, how we can get them, right? How we can get all the eigenvalue, because originally our question is this one, how we can get V1 until Vm, not just V1. Okay. So now let's answer the questions, how to get all the eigenvalue and eigenvectors. So in our case, we want to have S multiplied by V equals to lambda 1 multiplied by V1. So this is something that we want for one principal component, component. So if we want to have m equal to d, because if we have m equal to d, then we can reduce this later on, right? So if we want to have m equal to d principal components, so we want to have d principal components, how we can do this, right? So in this case, if you look at the dimensionality, this one is a d by d. Now d by 1, 1 by 1, 1 by d. Oh, sorry, d by 1. Okay, so in that case, if you want to transform it into m or d principal component, so this one have to be a matrix. So V1 factors become V a matrix. And this one also become V multiplied by lambda. Okay. So in this case, D is a D by D, and D here by M, but we know that M equals to D, right? So M equal to D actually. And this one is a D by M, and this one is M by M. But we know that all this actually M equal to D, because we want to get all of the principal components, the maximum one. I mean, in terms of the numbers is the maximum number of M. So in that case, to simplify the writing, so I just want to put all D. Okay. Any questions here? Okay, so if there's no questions, now the question is that how to solve this. Okay, so let me think how to solve this. Well, the easiest way, because now we just want to get the eigenvalue and eigenvectors. The easiest one is using SVD. In practice, we can just use SVD, single value decomposition. So in SVD, if we have S equal to U, D, and V, or V is already used, so W, for example, transpose. So this is the definition of singular value decomposition. So SVD again stands for singular value decomposition. Okay. So we know that if you use SVD, because this one is D by D, so because this one is D by D, it's much simpler. D by D is much simpler. Actually, W is equals to U if it is D by D. But anyway, so let's put in the standard form here. The columns of W means the row of W transpose, right? Are the eigenvectors of S, which is V1, V2 up to Vd. So this one U in this case is D by D. This one also D by D. This one also D by D. Okay, any questions here? Oh, by the way, you have to do this. In the assignment, you have to do this. So you have to know S, because S is again is known. This is known. Otherwise, we will not be able to do the SVD. Any questions so far? There is a question for Arunava. Arunava, if you want to know about details of SVD, I don't really have time today to explain SVD because it's just a tool that you can just call, right? But if you want to know further about SVD, you need to look at the internet. On the internet, Wikipedia has a very extensive coverage on SVD. So U is basically orthogonal matrix. So U, this one is a orthogonal matrix. And this D is a diagonal matrix. And W here is another orthogonal matrix. But for the complete picture of why this is U or how we can get this WDW is another topic, it's a big topic called SVD. Okay. Any questions here? Yeah, Darius mentioned that in this case, U equal to V, which is, yes, the V there is eigenvectors, that's correct. And D equals to lambda, that's also correct. D is actually the eigen value. And W transpose equal to V, no, W transpose is not equal to V. W equals to V. So W is again is the same as U. Okay, any other questions? Yes, okay, that's good. So now we know already, right? If you want to reduce the dimensionality, if you want to read M smaller than D, right? Well, it's very simple. As I mentioned, just remove them. So what it means by that is that if you have F1, F2, F3, F4, and then you have, for example, D equal to 5, FD, F5, right? So in this case, D equal to 5. And if you want to reduce M equal to 3, for example, then just take F1, F2, F3. Okay. Any questions? So there is a question from Nitin. Can we take any three factors? You have to find the largest. So this one is the first principle. Remember that you cannot escape from the intuition that we have in the beginning. In the intuition that we have in the beginning, we have to find this first. And then after we get that one, we find the second one. And after the second one, we find the third one. So can we remove V1 and start with V2? Well, we can, you can, mathematically you can. But your approximation will be very wrong. Because V1 is the first principle. The one that, you know, represents the most characteristic of your points distributions. Yes, so in this case, as I mentioned here, it starts from V1, V2, V3. V1 by definition is always the largest because this has something to do with the eigenvalue. Eigenvalue is always lambda 1 is always the largest. Okay, any other questions? All right, So if there is no questions, let's talk the practical side of this. The practical side of this, which is part of your assignment, is called eigenphase or eigenphases. I will explain later on, why these eigenphases are interesting, are important. But let's discuss the mathematics for this point of time. Okay. Okay. So assume that you have a phase image. A phase image means that you have an image with phase on it. So assume this is the phase, right? And the image has the dimensionality of width and height. This is your image. And then you have to do factorization. Means that you have to transform this into a factors. And this factor, it has the dimensionality of d by 1, where d here equals to w multiplied by h. Is it clear what you have to do here? You need to really understand this because this is part of your assignment. You have to do it actually in your implementation. So if you don't understand, it's better to ask. Okay, so I think it's clear, right? So you just have the pixel value now, the intensity. So you assume this gray. So this is gray image, grayscale image. So you don't have any problem here to convert into a vector. And this called xn. In our mathematical definition or mathematical discussion, we call it xn. And we have n phase images. We do the same thing. We do the same operation of factorization. And in the end, we will have xn bar n equals to 1 unto n. So we have n capitals of vectors. And each of these have d by 1. D here is quite huge, actually. So depending on the resolution of your image, the resolution of your image, D can be very large. If it is 100 by 200, for example, it's already 20K. D equals to 20K. All right. Any questions so far? So once you have this, the next thing you need to do, the step that you need to do, is to compute the mean, x mean, which is, as I mentioned, as we discussed, is sum over n xn. And again, this one is d by 1. Any questions for step 1? Okay, so step 2. You need to form S, where S again is d by d. So what is S? S equals to 1 over n, sum over n, xn bar minus x min multiplied by xn bar minus x min transpose. So this one is d by 1. This one is 1 by d. Any questions here for step 2? Again, this S is huge. Again, your dimension resolution is 100 by 200. Then this D will be 20K. So your S here is 20K by 20K matrix. Okay. All right. So then step number 3, compute SVD UDW transpose. So this one, as mentioned, the column of U or the column of W, the same things, are the eigenvectors. Any questions here? Okay.
Prof,
Yes.
this one we just use the toolbox, the tools to get the SVD.
Yes.
Right?
This is a SVD toolbox. Yes.
Okay. So in the assignment,
SVD function basically.
Oh, okay.
You just call SVD function.
Yeah. So it's allowed to use, right? I mean,
Yes. Yes. You can. The programming language that you have to use is MATLAB or Python.
Yeah. Okay. Just to clarify.
Okay. Any questions so far? Other questions? Okay. So if not, then number 4, convert back. All right. Convert back means that this one is a d by 1, d by 1, d by 1. So it's factors. You cannot see it, right? Because it's just a one long factors. So you convert back V1 to an image. Whatever you call it. This one is the first eigenphase. V2 is also have to be converted back into an image, and this is the second eigenphase. And then you can up to D if you want, right? If you want, you can have up to D, or if you want to reduce the dimensionality, reduce the complexity, you can up to FM if you want to reduce the complexity. Mth eigenphase. So that's all actually. This is called the eigenphases. All right. So now, if this is optional, but it is useful for you to check actually. If you can, I suggest that you do this step number 5. Step number 5 is called phase reconstruction. How we can use the eigenvectors is because of this phase reconstruction. So if you have xn tilde, so xn tilde is the approximation of xn. So this one, you want to approximate xn. You want to approximate xn, but you don't want to have, this one is a, have a, well, I will explain later on. Let's look at the phase reconstruction first. So xn tilde, to reconstruct back the xn, you have x min, right? And you have to plus this with U, which is the eigenvectors, right? And U transpose Xn, which is the original image, the original phase image, minus X min. This is what you need to do to reconstruct from Xn to Xn tilde using eigenvectors. Okay. So it doesn't mean anything here, of course. It's just transforming an image to another image, basically. Any questions? Okay. All right. So if there is no questions, so this is what you need to do in your assignment, right? So this equation, I didn't explain why we come into this equation, but if we have time, we will discuss the second derivation here. The second, we only discuss about maximized variance. We haven't discussed about this yet, minimizing error. If we have time, I think we can discuss this in the second session. So then we can have a full picture of this. But I'm not really sure if we have time though. Let me think. Because today the agenda is that we have to discuss about PCA, number one. Number two, we have to discuss about non-negative matrix factorization, which is NMF. And we have to discuss about LDA, linear discriminant analysis. Okay, so the problem is that this one is a part of the assignment, which we already discussed, finished now. And LDA is another part of the assignment. So I want to prioritize LDA first before getting into this one. But if you want to know about this one, you can look at the lecture note later on when I upload this into website, into the course, into Luminous, I mean. Okay, so, right, that's all I guess for this first session. If there is no question, then we have a break for 15 minutes. So we will start again. So start again at 7:40. All right. Thanks, everyone. So let's have a break. All right, so let's start our second session. If you can hear me, can you write something, please, on the chat?
Yes, Prof.
Yeah, thank you. Okay, so there is a question, good question actually from Nitin. So Nitin asked, when we do factorization, do we do it in row major or order or column? So yes, either of them is okay, because in any case, the weakness of this eigen phases is that the spatial information is destroyed because we do the factorization. So then the spatial information between pixels are no longer useful and are not used actually. And that is the one of the main drawbacks of this eigen factors. Eigen phases. So basically, what you do, most people do is to do it in this way, right? So this one is what most people do. But if you want to do it in that way, it's also fine. It's not wrong by doing that, but you have to be consistent. Okay, so there's a question from Nitin, and the other question that you might have in mind then, well, this one, the last equation that we write here, is basically just a replica, right? It's exactly the same. This one and that one is exactly the same. And in terms of the dimensionality, they're also the same. Means that actually this one is a d by 1, and this one is d by 1, and everything is d by 1, and this actually d by d. And what I mean is that this one, we use all the eigenvectors and all the eigenvalue. So there is nothing advantage here. I mean, there's no dimensionality reduction here. So now the question is that if you want to do the dimensionality reduction, what can we do? If you only have, if you use only Vm up to m, what is the advantage? How we can do that, right? So that's the question of dimensionality reduction. So to answer that questions, let's see. Let's put this in the next page. Sorry. Okay, so let's put it here. Okay, so if we want to do dimensionality reduction, how we can do it? Right? Okay, so we want to have m eigenvectors instead of d, where m is smaller than d. Okay, so again, I will not show the derivation here because of the time constraint, but I can just write here that xn tilde also x mean plus, if we want to use sum instead of matrix operation, this one is actually, let me see, m I, for example, I equals to 1 until m, right? Then this one is lambda I and vi. So this is another way to write. So if you want to have the replica or exactly the same image without approximation, so this one is without approximation, exactly the same, no reduction or anything, is exactly replica. But if we want to do the reduction, we have to write in this way first, right? Let me see. So in this case, let's try to understand this. It means that we only use up to m eigenvectors. And we also use this one, lambda 1 until lambda m. Okay, so this one, you use this v1 until vm. Okay, so what is the advantage of this? You have to pay attention on this. lambda 1 until lambda n actually the representation of your xn. So if you obtain this lambda 1 from, if you obtain this from xn, then this one will be representation of xn. In other words, your original xn, your pixel value here, it will be, for example, this one is I1, I2 intensity pixels value until ID. This is why you have D by 1. Okay. But if you use lambda 1, so again, this xn tilde, if you use xn tilde, well, it's not exactly xn tilde, but representation of this xn tilde, the reduction, the intensity reduction of this. So I'm not really sure what else that I can write. But if you have an image of vectors with lambda 1, lambda 2 until lambda n, they are actually the same thing. This one is a reduced, of course, a reduced representation. Yeah, this one is not exactly xn, but I don't really have another way to write it. So maybe hat, another approximation. Okay. So xn hat is actually m by 1. And this, as I mentioned again, representation of xn, because it's taken from xn, it's taken from there. So in this case, you can use, instead of using intensity here, you can use this one to represent the intensity of your image. So this is the representation of your image now. This is the representation of your image. So the dimensionality of your image now is m by 1. So now this one, the presentation of your image is m by 1 only. Is it clear? Any questions here? There is a question here from email. So the dimensionality of the image will be reduced? Yes, it is reduced now because m is smaller than d. Okay. And lambda 1 and lambda m, as I mentioned again, is obtained from SVD. You can get SVD, you can get lambda 1 and then lambda d actually from SVD. So, but this one, if you show this one, if you show x hat, right? If you show this one on your screen, it doesn't look nice. This one doesn't look nice. Doesn't look like a face. Doesn't look like a face. But if you transform this one into xn, into this one here, it will look like face. Very similar. Depending on m, if m is too small, of course xn will not be similar that much. But if m is considerably large, approximately similar to d, right? Maybe different only 2 or 3 numbers from d, xn will look very similar to xn. Xn tilde will be very similar to xn. So in other words, in terms of the visualization, xn tilde is approximation of xn.
Hi, Prof.
Yeah.
X mean the dimension is d times 1, right?
Yeah.
Then if you add to m, which is m plus 1, n times 1, then the dimension is really wrong.
Sorry again?
So we get the reconstructed one, which is the xn hat, right? Which is
So
m.
which equation? Equation 1 or equation?
The blue color. You highlighted in blue. In second
blue,
equation. Second equation.
The second here.
Yes, that's right. So we reduced it to become n cross 1, right? N by 1, right?
This is m by 1. This one is m by 1, yes.
All right. Then after that, do we need to add that mean again?
Oh yes, if you want. So this one, if it is m, right? This one is m, right?
Yeah, correct.
But this one the image have to be the same resolution. If you want to see the approximated image of the face that look like face, you have to have d by 1 instead of m by 1.
Okay, so if I want to get the reduced face, right? I just use xn hat.
X hat, yes, x hat. X hat is the reduced face, the reduced dimensionality of face, but it doesn't look like face.
Okay, so if I want to add x mean to x hat, my x mean must be m by 1 dimension also.
No, x mean is d by 1. It's this one. This x, m now is just there.
Then how do you add d by 1 with
So
n
this
by
one,
n by
everything here is d by 1. So this is a bit different from this A equation. A equation is a bit different. So if you want to write in the A equation, you can. So for example, if you want to write in the A kind of equation, so everything has to be the same. So this one is x mean, bar here is, this one is d by 1, this is d by 1, right? Plus u here is now changed, d by m. And this one, u transpose, is actually m by d. And xn bar is still the same, x mean is the same. Everything is the same. And now, but u is different now, right? D by 1, this one is d by 1. So in other words, that the whole things here is d by 1. So your reduced dimensionality cannot be seen in this image, in this in this equation. Your reduced dimensionality is actually hidden inside here. So inside this one, if you multiply this one give you your lambda. This one give you lambda. So lambda here, lambda is a factors, which is eigen value. Sorry, is that no lambda? Let me see. This one should be m by 1. So the whole thing, if you multiply.
So that is
m by 1.
X hat, is it?
This one is yes, xn hat.
Okay. Then I understand. Yeah, thank you.
Yeah.
Okay, correct. Yeah.
Okay, so don't confuse between x hat and x tilde. X tilde is what you want to see. Reduce approximation. This one is approximation. But the dimensionality is still the same, d. If you want to have a reduced representation, that will be, this one is a reduced representation, reduced dimensionality. Reduced dimensionality representation. Then if you want to reduce the dimensionality for in your representation, you have to use x hat. Any questions here?
So can I say that the purpose of getting x hat is so that we can train our model like with less consumption, is it?
Exactly.
Like
exactly. Yes.
So instead of using like the original image, which is like have a very high resolution,
yes,
we just use xn hat, which is computationally lower.
Exactly.
And we get the same result.
Yes.
Okay, thank you.
Yes, this one will be used when we discuss LDA. In LDA, the metric is so big, so you don't want to have and the metric can be singular metrics. So you want to do this PCA first to get x hat, and then you operate your LDA. Because this one xn is actually representation of your xn hat is again xn hat here is the representation of your xn, original xn, in reduced dimensionality.
All right, thank you, Prof.
Okay, any other questions? So there's a question here from Nitin. Lambda m is a Lagrange multiplier. Yes, Nitin, in the beginning, it was a Lagrange multiplier. So in the beginning, very beginning, it was a Lagrange multiplier. So this one. But we know now another meaning of this lambda is actually this one, which is the eigenvalue. Okay, so there is a transformation of the meaning here. So, and you need to be careful. Okay, so the discussion here is also important because this one is the point of using PCA in dimensionality reduction, especially for your phase representation. Before I continue, any questions? Okay, so let's discuss this a bit more intuitively. So I will share with you the slides. So this slide is taken from Prof. Feng. So Prof. Feng is the previous instructor. So here, so for example, this phase, right? And then we have raw data, and then we have to have a representation of this, and this representation of features, and then we can do the recognition after the features. So your lambda is actually your features. That's why you can play with your lambda. When lambda is up to D, for example, then you don't have any reduction in terms of the representation. But if lambda is up to M, then your representation is already reduced, like what one of you just mentioned in the discussion. Okay, so anyway, so I will just skip this one. I just want to go immediately directly to the intuition of this. So everything here is the same as what I explained to you before. Okay, so how this eigenfaces look like. So this is how eigenfaces look like after you convert back into an image. All right, so this one, the left corner here is the mean, the x mean. This one is x mean. And this one is the first eigenvalue, eigenvectors, the second eigenvectors, the third eigenvector, the fourth, and so on. So this is the intuition of your eigenfaces. Any questions here? Okay. So this one is the reconstruction, as I mentioned. So you have this reconstruction of xi. Xi is the input image, and xi here is your approximation. Okay. So it depends on how many dimensionality of P here. P here is the same as our M. So P here equals to M. Okay, depending on that, we will see the approximation. So for example here, if you just use, so this one is the target phase. So this one, if you use all of the P equal to D, then this is what you get. So this phase is what you get. So this is the input. So this one is xi. And if you just use P equal to 1 or P equal to 0, I mean, for P equal to 0 means that you just use the mean, x mean here. And that x mean is actually this one. You can only get this phase, which is the average phase. And if you use P equal to 1, which means that you use 1, the first eigenvector, you will have this one. If you use the second and the first, then you get this one, and so on and so forth. So this is adding one more eigenphases in sequence. So this one is 1 by 1. If you just skip this into 8 8 eigenvectors, 16 eigenvectors, 32 eigenvectors, 64 eigenvectors, and so on, then this is the evolution of the phase. The more number of factors, eigenvectors that you use, or eigenphases that you use, the more accurate xi will be. So this one is xi tilde. In the end, you will not, these two actually, you will very difficult for you to differentiate between these two. But this one is actually use less eigenphases, less eigenvectors. That's why you can reduce the dimensionality. So for example, you think that, okay, so up to these eigenvectors is already accurate enough, so I don't really care about the details, then you already reduce your representation. Okay. Any questions? And this is useful for transmitting your data actually. If you transmit your data, first you just once you send this x min only once. The next you just send this eigen values, and eigen values actually smaller in terms of the dimensionality compared to your original pixels. Does it make sense? Okay, any questions?
Hi, Prof.
Yes.
So can I just ask if this method is actually used practically for example, compression?
Yes, compression can be used as well. Yeah.
Okay, cool. Thanks.
Yeah. So yes, many of the compression methods use basis function PCA to do the compression. Okay, any other questions? Okay, so this is your assignment, the first part of your assignment to construct these eigenvectors. Okay, so if there is no question, let's move on quickly to the second topic today, because we don't really have that much time. Okay, so the second topic is non-negative matrix factorization. So the second topic is NMF, which is a non-negative matrix factorization. Okay, so what is the motivation here? The motivation is that it's followed exactly the same as in PCA. So this is actually the extension of PCA. In PCA, we can have the representation of our approximation of a data xn equals to x min, the average phase, or the average the mean of the average values, plus I equal to 1 until m. So m here smaller than d. So assuming that this one is d by 1. And this one is lambda I, the eigen values. And this one is the eigenvectors. Again, this one is a d by 1. Now, the problem in eigen phases or eigen PCA in general is that these two values, either eigenvectors or eigenvalue, can be negative. And in some application, negative values is really not intuitive. So this one is not intuitive. Because most of the cases, the data are positive, but then lambda I and VI, some elements of VI, can be negative. So this non-negative matrix factorization just to make this positive, to force, the idea is to force. So idea to force lambda I and Vi to be positive. So this is the main idea. And this is used a lot actually in some application, and NF is more accurate than PCA. The basic idea is similar, means that we have the mean. So for example, if you want to have X is all the data that you have. So this one is D by N is the number of your data, minus the basis V. So no, previously we used V. So B here is actually V that is positive, V that cannot be negative. So that's B, but basically the same as V. And lambda here, lambda is also positive. Okay, so this one is square, and this one, the whole thing is D by N. Let's put it in this way, D by M, because we reduce the dimensionality, and M by N. Okay, so, and this one is subject to Bij, the elements of matrix B greater than 0. So this is the, the constraint, and lambda, the same lambda Ij is also greater than 0. Oh, by the way, because this is a matrix, so this is a matrix, right? This one is a matrix. So a matrix you cannot square. So in that case, you have to change this into a norm, and the norm here is called F, which is stand for Frogenous norm. So this is the Frogenous norm. Basically, Frogenous norm is very simple. You have the integral, the square root of, in this case, there will be some sum here, I think, of x. There are two sum, because we have D and N. This one is X, so let's put this one Ji. Ji is up to D, J is up to N. Xij minus Bij multiplied by lambda Ij, right? Square. So this is basically Frogenous norm. So this is actually the definition of Frogenous norm. And you square this means that you remove the square root. In the end, you have only the inside one. So in the end, you only have the one that inside, because the square root will be cancelled by the square. That's the meaning of this equation. Any questions? So there is a question from email. P is SVD of V. No, as I mentioned, P is the same as V. It's the same. I can write as a V, but it has to be positive. Okay, any other questions? Okay, so if there's no question, now the question here is that how to solve this, right? How to minimize. Well, to minimize this one, you can have the same idea that you can have J is this equation, okay? So divided by B, for example, equals to 0, and Dj divided by D lambda equals to 0. So what is J? J is this whole thing here. J is this one. Okay. So I will not go to the details. You can look at the lecture note later on, because I don't have time too much on describing this. But the problem of this is not closed form. It is not equal to 0. You will find this cannot give a closed form solution. So then if you cannot give a closed form solution, what do you do if you cannot have this solution to be in a closed form? A closed form means that Bij equals to some function, right? So equal to x in this case. So Beg equal to function of x, which is the x is the input. So we cannot have this closed form. So if that is the case, what should we do? Anyone? Yes, you use gradient descent. You use gradient descent. So that's basically the idea here. You use gradient descent, you know gradient descent, right? So for example, if I use this one as an example, so lambda Ij new, for example, equals to lambda Ij old minus lambda alpha, alpha Ij multiplied by Dj multiplied by D lambda Ij. Okay. And if there's any Ij here, lambda Ij equals to lambda Ij old. So basically this is called gradient descent. I will not explain this because I assume that you learn this kind of concept from other courses. But this is called gradient descent. And gradient descent has a problem with this. It means that it can swing. The optimization can swing because you know, if it is too large, if alpha is too large, if it is too large, then the optimization can swing, means that you cannot converge. The optimization cannot converge. The error of this new lambda will not converge. So that's called swing into the minimum. And if alpha is too small, what happens then if alpha is too small? Anyone know about gradient descent? If alpha is too small, it's slow. That's correct. So to solve this problem, what will be the solution? What will be the immediate solution? Yes, it's a proposed. It's proposed 300, 400 years ago by Newton. So Newton already knows about this problem, and the solution is called Newton methods. So NMF here use Newton method. So they use Newton method instead of gradient descent. Okay, so that's the basic idea. And in Newton methods, alpha Ij equals to what? Anyone knows? Or we replace alpha Ij in Newton methods? Yes, Hessian. Basically, Hessian is the second derivative. So this one is, if you use a single variable, not matrix or not factors, then it will be d square j d lambda ij square, which is, this one is actually Hessian. If you use the factors, then it will be Hessian matrix. Okay, so that's the basic idea of this NMF. Any questions so far? Yan Xuan, I'm not really sure. What do you mean by we will face the problem of stuck in lock? Oh, I know. You mean this gradient descent? Yes, this gradient descent can be. Yes, this local minimum can be a problem. That's true, and there is no solution proposed in the NMF. So the problem of this is called initialization. How we initialize this, right? Well, the idea is that you can initialize using I think you can use PCA for initialization. And once you have the PCA, then you force this to be non-negative. All right, any other questions? Okay, so if there's no questions, that's for the non-negative matrix factorization. So we move to the next topic. So this one is lecture 7C, which is LDA. Okay, so LDA, as I mentioned earlier, is stands for linear discriminant
Prof,
analysis.
what do you mean by use initialization PC?
Okay, so this one is actually part of the optimization. So again, this one is part of the question is actually an optimization question. So in optimization or minimization here or maximization, basically you have this kind of graph. You can, this is error. Error here means like a J in our equation here is J. J is the error, right? J is the error. So this one is a error or J. And actually we want to have J to minimize J to means minimize J with respect to, for example, here, what is the lambda, for example, lambda 1 with respect to lambda 1 or lambda ij, for example, then this one is lambda ij. So we want to minimize J with respect to lambda ij, right? Means in the end of the day, we want to have this basically. This is the minimum one. This is the minimum error. Okay. That's the goal, right? In optimization.
Yeah.
Now, if you use gradient descent, assume gradient descent, which is the simplest one, you can initialize from here. This is initialization. Means that your value of lambda ij old is this one.
That's right. Yeah.
And then you do the optimization, means that you rolling down this initialization value, right? Until you get this, hopefully. If your alpha is correct. But if your initialization is here, so this one is your initialization, means that lambda ij old is there, then what happened? It's rolling down, 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 up to here, and then stop. This is called local minimum. This is called, this one is called global minimum. Does that answer your questions?
My question is like, how do we use PCA to get the better
Yeah, so
initialization?
PCA, well, instead of random, you have this from PCA. You use PCA first to get that lambda ij. Lambda ij is eigenvectors, right?
Eigenvector.
Eigenvalue.
Eigenvalue.
Yeah, eigenvalue. You can use PCA to get the eigenvalue.
Okay. All right. Thank you.
Okay. Any other questions? All right. Okay, so now let's move on quickly to LDA. LDA is a very different approach to PCA. Basically, this is a discriminant, means that it's actually for classification. Now, what is LDA in terms of the concept? Assume that you have two classes of point, red and green. Let's see if I, that's not really good. Okay, so it's fine. So red is green. Okay, right. So basically, LDA concept is about projection. What will be the best projection? So if you do the projection, for example, for this, if you use histogram, you will have this representation here, right? For the red one. And then you have the representation for that one, which is good in this case. Then you can separate the two classes. You can separate them with this line here. Problem solved. Okay. So, but what happened if you have different types of distributions? So what happen if you have this kind of distributions here? And this one is your green. So in this case, if you do the same projection again, then it will overlap. And if it is overlap, and if you do the classification, it will be wrong. For some point, it will be wrong. Okay. So the basic idea of LDA, which is found 100 years ago by Fischer's, is that we want to project this into more proper projection. So more proper projection is that we want to project somewhere here. So then we can have the histogram of the red one and the histogram of the green one in a different location. So that's really the basic idea of LDA, the intuition behind LDA. We want to find this line here. We want to find this line. And this line has two properties. One, the interclass. So this one is interclass. So this one is interclass. The interclass distance has to be minimum. So the interclass distance has to be minimum. Interclass minimum. Sorry, not interclass, intraclass. Intraclass has to be minimum, but the interclass is mean that between the class or between the class has to be maximum. So this is two basic idea of LDA. The interclass, we want to minimize the interclass variations, and we want to maximize the interclass distance. So again, I repeat, maybe I give you a wrong impression, a wrong sentence. We want to minimize the distance between minimize the distance of the point in one class, and to maximize the distance between different classes. Okay, so that's really the basic idea of LDA. Any questions? Okay, so if there is no questions, okay, so let's consider two classes first. So this one is two classes. Actually, we will expand this into more than two classes later. So let's, for now, only consider two classes. So let's assume that we have the mean. Okay, so let's assume that we have the mean of each of the classes. So let's assume that we have the mean here. Let's have some blue color here. So let's assume that the blue color is the mean of the red. So this one is a mu1 is the mean of the red points. And let's have this green point as mu2, the mean of the second class, the second points, the mean of the second class, yes. So in that case, we have mu k equals to, k is representing 1 or 2, the number of classes. So k here is either 1 or 2. 1 over n, the number of the data for each class, where n is the set of k, of class k, and we have xn bar. Any question here for the mean? So basically, this is the same like what we discussed x mean, right? But if I use this x mean, I cannot use k. So that's why I don't really like this one now. Anyway, so this one, again, if you look at the dimensionality, this is d by 1. So this one is d by 1. And we want to project this. We want to project this blue line. We want to project this into, let's see if I can use another more obvious color. Let's use blue here. So we want to project this, the mean, into that blue line. And there is a blue line here. Blue dots. And let's call that blue dots M1. The same for the green one, the green dot. If I project that into that blue line, it will be a point there on the blue line. And let's call that one M2. Okay, so with this, then we have MK. So I'm not really sure what is the dimension of M here yet. So let's have MK equals to the projection, which is called W. So W is a factor that transform, that project the points into a certain plane, into a certain line. In our previous discussion, we use V, right? So, but it's not eigenvectors anymore. So I use W instead. Mu K. So this is called projection. The projection of the mean. So if you look at the dimensionality here, actually, mu K is d by 1. W is the projection, is 1 by d. So mk is actually 1 by 1. So I don't need to have the bar. Any questions so far? So there's a question from Nitin. Are we considering that there are endpoints in each classes? Yes, that's correct, Nitin. Okay, any other questions? Okay, so if there's no questions, as I mentioned, in terms of the variance, there are two types of variance. As I mentioned again, there are two types of variance. One is within class, and the other is between classes. So this is what I call intra-class, inside the class. Then this one is inter-class, between classes. So let's look at number 1. So number 1 is variance within a class. So again, this is the same as what we discussed before. So S is the variance, SK square is the variance, equals to sum over n subset of this class, the number of point in that class, yn minus mk. Again, mk is the projected mean. So what is yk? In the picture here, so this picture is a bit not really obvious, so I draw it again here. Let's see if I can draw. So okay, red point and green point, and then you have blue line, and then this one is a mu1, so this one is mu1, and this one is mu2, and the projection of mu, the projection of this mu is called m1, the projection of this there is m2. So yn is the projection of the sample, so each of the sample is projected there. This is y, for example, this is x1, this is y1. Okay, so that's the projection on that blue line. We do not know the blue line. That's something that we want to find actually. Okay, so what is y and n then? Yn is the projection. When we say projection, we always use w, right? Transpose xn. So this is a projection of xn using w to the line, to the blue line. So this one is known, this one is known, but w of course is unknown. Any questions so far? Okay, so the total variance will be S1 square plus S2 square. All right, so this is variance within class. Now let's move on to the second definition of variance, variance between classes. So this one is basically, if you look here, if you look at these pictures here, in variance, a variance between class means what? What we want to maximize here? Anyone? What do we want to maximize in this graph? Yes, M2 and M1. So that's correct. So we want to maximize between M1 and M2. The distance between M1 and M2, we want to maximize that. So variance between class that we want to maximize means that we want to maximize B square, with B square is M2 minus M1 square. Okay. So now, based on these two definitions of variance, there is a notion called Fischer Criteria. So Fischer Criteria, J of W, because W is something that we want, right? The projection is something that we want to know, equals to B square. So because we want to maximize, so remember we want to max this one, we want to maximize over W. So we want to maximize, let's see. So we want to maximize J of W, and J of W should be defined using Fischer criteria, which is B square divided by S1 square plus S2 square. So in other words, we want to maximize this one, and at the same time, we want to minimize this one in order to maximize J. All right, so this is very important. So this is the starting point of our discussion. Any questions here? Any question, anyone? If you don't understand, please ask. Again, this is part of your assignment. So there's a question from Kai Yang. What is W? Okay, so I will repeat here. So we have this distribution of point, right? So assume that we have imaginary line, blue line. And we do not know that blue line, of course, but assume there's a blue line there. We want to project this dot, the mu1, into M1. And this projection is done using W. And the W here will be the same as W here. They are the same because the projection is in the same direction. So there's another question, Nitin. Yn is a factor. Well, we see. I haven't defined this. Let's see. I think it's not. W here is 1 by M. Sorry, 1 by D, because this one D by 1. So this one is 1 by 1. Any other questions? So
the W is from SVD or something?
No, W is not from SVD. There's no SVD here yet.
Where you get
W is a transformation, projection. You don't need to know now because we do not know what W is, but W is, it's a projection. If you have, that's what it means by projection. So I give you the idea of projection. So, for example, if you have a point here, right, and then you want to project that into this location there, what do you do? Using what is yes, using cos, or the other. If you don't want to use cos, you use what? Use dot product. Yes, you use dot product. And this one is a dot product, the same as dot product. This one is actually W dot xn, the same. Why they are the same? Why they are the same? Well, if you have W, for example, 1, 2, it is W bar, and dot product xn is 3, 4, is the same as W transpose 1, 2 multiplied by 3, 4. They're the same thing, right? Because you multiply this one with that one plus this one with that one. The same here, to multiply with that one plus this one multiplied with that one. They're the same.
So how do we get the W if it's unknown? So
W, as I mentioned, we do not know. W is something that we want to know. W is unknown. But you can imagine that, right? If there is some projection, then that should be described in this way.
Yeah.
Right?
Right.
Okay, any other questions? Any other questions here? Okay. This one, by the way, is actually W xn cos theta, right? So you know that this one is theta. But anyway, so I suppose you know this because you are master students. Okay, so now we have this one. We want to maximize the variance between classes and to minimize the variance within class, which is the denominator. So for this Fischer criteria, any questions? Again, we do not know W. W is something that we want to find in the end. We want to find the projection.
So Prof, at this point of time, we just say that W is just a projection. At the end of the day, we will find W.
We will find the projection. Yes, we will find. We try to find the projection.
So we will find a W, then we will know where are we plotting, where are we
Exactly. So
projecting.
if you know W, you will know that this one, for example, using the first problem that we have here, so this one will not be chosen. So this one will not be chosen because this one is not maximizing J. And in the end, it will be this one because this one will be the maximizing J.
So ultimately, we are finding W so that because the blue line can be projected at everywhere, right?
Yes.
So we find the W to project to a certain location such that we can classify them correct.
Correct.
All right, thank you.
Yes. Any other questions? Please ask your question if you don't understand, so then you can follow the discussion. Okay, so if there is no questions, so let's look at this. P square equals to M2 minus M1 square. And this one is a scalar. And we know the definition of this, which is W transpose of the projection factors multiplied by mu2 minus mu1. So this is by definition, right? By definition, this is what we have. Again, this is 1 by D. The whole thing here is D by 1. It's the same as M2 minus M1, which is 1 by 1. Okay, so if we consider this further, so again, I think you remember that A B square equals to A square B square. Okay, so let's follow that one. So if I abuse the notation, so if I abuse the notation, this is not a correct notation, but it will make it clear, actually. It will be W transpose square multiplied by mu1, mu2 minus mu1 square, right? It is not a correct notation, of course, because this one is of factors, this one is of factors, this one also factors. You cannot square them. So the correct notation should be W transpose multiplied by, so let's multiply by mu2 minus mu1, mu2 minus mu1 transpose multiplied by W. So this is the correct notation. So in this case, it will be 1 by D. So the whole thing here is D by D. This one is D by 1. Any questions? So the whole things here is the most important part. Is we represent that with SP. So again, SP is D by D. Any questions? Okay, so if there is no questions, let's continue our derivation here. So let's look at the S1 square plus S2 square. This one is if you have a number of points in class 1, so this for the whole points in class 1, you have yn minus m1. So this is the variance definition, right? The variance definition that we discussed before, plus sum of C2 yn minus m2 square. So this is the definition of the variance. So this one, if you recall, is the same as this one here. this one. Okay. So I just copy and paste basically. So I just copy and paste here. Any questions? Okay, so if there is no questions, let's continue this derivation here. So sum of a C1. So we do the same. W transpose Yn is a W trans. So Yn here is W transpose Xn minus W transpose mu1 square plus sum of a C2 W transpose Xn minus W transpose mu2 square. No problem here, I guess, right? This is just by definition again. Okay, so now let's have this trick. W transpose Xn minus mu1 right, square plus C2 W transpose Xn minus mu2 square. So again, there's nothing special here. And now this transformation is independent from C, independent. Because W is not dependent on the samples point. Okay, so this one is also independent from that one. Any questions here for the notion of independent? So if it is independent, then W can go out from the sum. So W transpose multiplied by sum of a C1, then you have Xn minus mu1 multiplied by Xn minus mu1 transpose. So this is the definition of square, basically, right? Plus, let's see, plus C2, same, Xn minus mu2, Xn minus mu2 transpose. Any questions so far? If you don't understand, please ask. Okay, so if we have this, again, we can take these whole things as S, matrix S. So then we have W transpose S W. W means within. So this one means within. This one is within. Multiplied by W. So if you look at the whole thing, so this one is actually 1 by D. This one is D by 1. The whole things here is D by D. So SW is D by D. So if you combine this definition and the previous definition here, then the Fischer criteria is that J W bar equals to P. P is a W transpose SPW. So P is W transpose SPW divided by the second one, which is W transpose SWW bar. So remember that we want to, so this one is the important equation. And we want to maximize. Any questions so far? Any question, anyone? Okay, so if there is no questions, we want to optimize this or to maximize this optimization, or in this case, it's a maximization. And the optimization, how we can optimize this, anyone? Any idea how to optimize this? Anyone? Minimax? Not really, not minimax. It's the same again. It's basically the derivative of J with of W bar. Yes, this is a differentiation again of dW bar equals to 0. Okay, so this is something that we need to solve. And I think to solve this, now this one is actually the derivative of x. For example, you have u of x, ux here, u of x, divided by vx. So what is the rule? Oh, well, it's a bit complicated, so it's very difficult to write on the chat. So this one is a v du minus u dv divided by u v squared. So in this case, in our case, u is W transpose SP W, and V is W transpose SW W bar. Well, it is a long equation, basically, right? So if you do this operation, it will be long. And there are still a few steps to solve this problem. There's still a few steps to solve this problem. But in the end of the day, so we will discuss the details next week. So by the end of the day, we will have an equation SW W bar equals to C1 divided by C2. So this is a constant. So this one is actually a constant. So you can put it in as C actually, because both of them are constant. SP W bar. So in the end of the day, we will have this equation, and this equation, from this equation later on, if you want to really know W bar, for example, is a proportional, because we do not know C. It's a magnitude. C represents the magnitude, but W actually you don't need to know the magnitude. You only need to know the direction. So even we have something that is not absolute, it's still fine, because we can get a W, the direction of the projection. So this is the end of the day. So we will know the direction of the projection, because we know the relative value of W. We do not know the magnitude, the correct magnitude of W, but we know the direction. Okay, so in other words, if we use this as unit factors, then we will know the direction of the projection. Okay, so there are a few different steps here. So from this to that one, from this one to that one, so I have a few steps, and we will discuss these few steps next week. Any questions? So if there is no questions, right? So what is the important things? So again, my portion in this module is actually only 2 weeks. So this week and next week, and next week after that, there will be another instructor. Okay. So my portion, I will teach you the main things is a PCA. The second thing is LDA. Of course, there is a modification, extension here on NMF, right? But this is just a small bit. So LDA, and then the third one is SVM. So next week, I will try to finish SVM. So I will try to finish LDA, and then I will quickly move to SVM. We don't really have that much time because all this have to be done in only 2 weeks. Okay. Okay, so are there any questions? So there's a question here from Nitin. What is C? Don't worry about this, Nitin. We will discuss this next week. So as I mentioned again, C is a constant. Constant because this W need to have magnitude. That constant, the correct location of this line is basically based on that C. But we do not know C, so then we have to make W as a unit vectors. So then we can only know the direction. Okay, so this is the plan. Any questions? Any other questions? Okay, so if there is no questions, that's all today. And thank you. And hopefully you have a good night.